Hello guys, welcome to my channel. Press the subscribe button like this, and then you have to tap the bell icon adjacent to the subscribe button like this, and then you will get the notifications from my channel.
Hello guys and welcome to my channel. In this video I'd be explaining you multiple questions on refrigeration engineering. So directly let's start with the video without wasting any of the time. So the first question, it says a Carnot refrigerator requires 1.5 kilowatts per ton of refrigeration in order to maintain a region at a temperature of minus 30 degree Celsius. So find the COP of the Carnot refrigerator. So COP directly of the Carnot refrigerator you have to find. So directly go with the basics of the formulas, that COP, it is equal to refrigeration effect upon the work input. Now you have to find these two values, right, in order to get the COP value. So if you read the question again carefully, it says that the refrigerator, it requires 1.5 kilowatts. It requires means the work input is 1.5 kilowatts per ton of refrigeration. So that means for 1 ton of refrigeration, that is refrigeration effect of 1 ton, we require 1.5 kilowatts. So directly we can say the refrigeration effect for 1 ton of refrigeration, 1 TR, we need 1.5 kilowatts of work input. And I have already explained in my previous videos and also derived that 1 TR is equal to 3.51 kilowatts. So if you have not watched that video of derivation, I have given the direct link in the video description. You can go and watch that video. So you can directly substitute 1 TR is equal to 3.51 kilowatts whole upon, again it is 1.5 kilowatts only. Kilowatt get cancelled. This value, if you solve, this will come out to be 2.34, which is very near to 2.33. Hence the answer is B part. Answer is option B, 2.33. I hope this is clear. Let's move on to the next question. In a certain ideal refrigeration cycle, the COP of heat pump is 5. A cycle under identical condition running as a heat engine will have a efficiency as. So again, go with the basics. I'll tell you one thing, that COP of a heat pump, it is equal to T1 upon T1 minus T2. Just for reference, I can say COP of a refrigerator, it is equal to T2 upon T1 minus T2, where T1 temperature, it is the temperature of the sink, T2 is the temperature of the source. So this is the COP formulas for a ideal Carnot refrigerator. Okay, it is saying in the question that COP of a heat pump is 5, so you can equate this value equal to 5. What we have to find? We have to find the cycle running as a heat engine under identical conditions, so it will have efficiency as, so we know the efficiency of a heat engine, reversible efficiency of a heat engine, of a reversible heat engine, it's a 1 minus T2 by T1. This is the efficiency formula. So all we need is T2 by T1 value. So in this equation, if you divide the numerator and denominator by T1, so it becomes 1 upon 1 minus T2 by T1, it is equal to 5. This you cross multiply, so 1 minus T2 by T1 will be equal to 1 by 5. 1 by 5 is nothing but 0.2, it is equal to 1 minus T2 by T1. So what I have taken, this entire I have taken that side, and 1 divided by 5 is 0.2, it is equal to 1 minus T2 by T1. And this value itself we need to find, right, 1 minus T2 by T1, or like directly we are saying it is equal to 0.2. So you can write equal to 0.2. So efficiency of heat engine is 0.2. Or other way, if you are not understanding, then if you are just going with the exact basics, find T2 by T1 value, then bring it this side, it will be 1 minus 0.2, it is equal to 0.8. Put substitute value of T2 by T1 equal to 0.8, again 1 minus 0.8 is 0.2. Here you are directly seeing that this efficiency of heat engine is nothing but 1 minus T2 by T1, that is this entire value, it is equal to 0.2. So 0.2 is the answer. Again answer B part. So I hope these two questions are clear. Let's move on to the next question. The coefficient of performance of a refrigerator working on a reversible Carnot cycle is 4. The ratio of the highest absolute temperature to the lowest absolute temperature is. So go with the basics. The coefficient of performance of a refrigerator. So it is saying COP of a refrigerator operating under Carnot cycle, reversible Carnot cycle is 4. So this is equal to, I have already explained in the previous question, the formula I have given as T2 upon T1 minus T2. Now what we have to find? We have to find the ratio of highest absolute temperature. So highest absolute temperature, it is T1, that is the ratio, and that is the temperature of sink, 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 and T2 is the temperature of source. So we have to find the ratio of highest absolute temperature, that is T1 upon T2. This value we have to find as the calculation. Okay, this ratio we have to find. So this equation we have 4 is equal to T2 by T2 upon T1 minus T2. You divide this equation by T2 on numerator and denominator. So you will find it equal to 1 upon T1 upon T2 minus T2 by T2 is 1. It is equal to 4. Cross multiply, so it will be T1 upon T2 minus 1. It is equal to 1 by 4. 1 by 4 is nothing but 0.25. So T1 by T2 is 0.25 plus 1, that is 1.25 is equal to T1 by T2. This you have to find T1 by T2. So you got the value 1.25. That is the answer. Again B. Okay. So let's move on to the next question. I'll just take a 2-second break just for you to see. Okay. Now I'll move on to the next question. The thermal efficiency of a Carnot heat engine is 30%. If the engine is reversed in operation to work as a heat pump with operating conditions unchanged, then what will be the COP for heat pump? Okay. So what it has given? It has given that the efficiency of a Carnot heat engine, it is equal to 0.3. Okay. Then if the engine is reversed in operation to work as a heat pump, then what is the COP of heat pump? So basically if you go by this formula, so we know that 1 minus T2 by T1, it is equal to 0.3, because the efficiency formula is 1 minus T2 by T1. What we have to find? We have to find COP of heat pump. COP of heat pump is nothing but T1 upon T1 minus T2. Okay. So from here we get the formula of T2 by T1 is equal to 0.7. This you keep as separate first equation. So COP of heat pump will be nothing but COP of heat pump, it is equal to, you divide numerator and denominator by T1, you will get 1 upon 1 minus T2 by T1. So if you substitute, you will get 1 upon 1 minus T2 by T1 is 0.7. So it is equal to 1 upon 0.3. So 1 upon 0.3 equal to 3.33. This is the COP of heat pump. Here one important deduction that I want you to know directly, that if they have given the Carnot heat engine efficiency, so from this equation you see that COP of heat pump is nothing but 1 upon 1 minus T2 by T1, and this entire term 1 minus T2 by T1 is nothing but efficiency of a reversible heat engine operating between the same temperature limits. So from this we can deduct that we can write a corollary equation, that is COP of a heat pump, it is equal to 1 upon reversible heat engine directly. So if they have given this value, just 1 upon that value, you will directly get COP of heat pump. And another equation that we have is COP of heat pump minus 1 is equal to COP of refrigerator. So COP of refrigerator, if they would have asked, then directly minus 1 if you do, you will get 2.33, because that equation that we have separate is COP of heat pump, it is equal to COP of refrigerator plus 1. This is another equation that I have already derived in one of my other videos. If you want to see the proof, you can go into the description of the video, you will find this video as well, direct link, you can watch this video as well. So if they are telling in the question to tell us the COP of refrigerator, you find COP of heat pump, that is equal to 1 upon efficiency of heat engine, and you subtract minus 1, that is you will get COP of refrigerator. I hope this is clear. So I'll wait for 5 seconds for you to see how it is done, then we'll move on to the next question. Okay, let's move on to the next question then. A heat pump is used to heat a house in the winter and then reversed to cool the house in the summer. The internal or the inside temperature of the house is to be maintained at 20 degrees Celsius. The heat transfer through the house wall is 7.9 kilojoule per second, and the outside temperature in winter is 5 degrees Celsius. What is the minimum power required to drive the heat pump? So directly, if you can do directly, but I'm just making a small figure to explain. Suppose this is the internal surface of the house, this is the wall that is separating internal and external, basically the environment. So environment, it is saying that it is at 5 degrees Celsius, it is at 20 degrees Celsius. So it is working as a heat pump. Heat pump means in order to warm the internal space. In winters, we have to keep internal house warm as compared to the outside. So outside we have low temperature in winters, and inside we need more higher temperature. So we use a device known as heat pump. So heat pump will add heat equal to 7.9 kilojoule per second, that is kilowatts. This much amount of heat it is adding. So what is the minimum power required? We will go by the formula, that COP of heat pump, it is equal to T1 upon T1 minus T2, which is further equal to the refrigeration effect or the heat that is being flowing. We will not say refrigeration effect, we will say the desired effect, because here the heat is transferred, so we can say directly Q by the work done or the power input that we need. So from this formula, we know this value, we know all the other values, we know Q, we can find W. How we can find? I'll tell you. We can write T1. T1 is nothing but 20 degrees Celsius, because for heat pump T1 is the sink. So finally sink value is 20 degrees Celsius. So you add 273 in order to convert it into Kelvin. So it is 20 plus 273 whole upon T1. Again 20 plus 273 minus bracket 5 plus 273. Okay, that is equal to Q upon W. Q is nothing but 7.9 kilojoule per second, so it is kilowatts. So you have to be careful with the units. By W the work done. So here on the left side, if you see on the numerator, it is Kelvin. Denominator, temperature minus temperature, is again Kelvin, so this is having no units. Similarly, on the right side we have the unit equal to kilowatts, so the direct answer for W, it will come into kilowatts only. So what is the answer? How you can do? You can directly straight away solve. So I'll just solve quickly and then let you know the answer. So 20 plus 273 is 293. You can solve along with me. 293 divided by, so no need to go in this one. So 273 and 273 get cancelled, so it is 15. 20 minus 5, 15. So divided by 15, that is this value, and then W is 7.9 divided by 19.53. So finally what you get? You get you get W value equal to 7.9 divided by 19.53, that is equal to 0.4 kilowatts, 404 to be precise kilowatts. This is the minimum power required in order to drive the heat pump. So I hope it is clear. Okay, so I'll again take a 5-second pause for you to see, then we'll move on to the next question. Okay, now we shall move on to the next question. So this is basically a paragraph type of a question in which one question is there, then out of those further 2 questions arrive from that particular data. So this is based on vapor compression refrigeration cycle. So if you are not aware of how the vapor compression refrigeration cycle works, its theory, its questions separately, then I have already created videos on vapor compression refrigeration cycle, actual vapor compression refrigeration cycle, numericals on vapor compression refrigeration cycle, Bell-Coleman cycle, and then psychrometry. All those I have already made videos, and you will find the direct video links in the video description. So I'll not explain in detail what is the basics of vapor compression refrigeration cycle. I'll directly solve the question here. So if you are not knowing the basics, I suggest that you go and watch those basics concepts, that what is evaporator, how the cycle works, and all those things. Okay, so here we have a refrigerator based on ideal vapor compression cycle operating between temperature limits of -20 and 40. Refrigerant enters the condenser as saturated vapor and leaves as saturated liquid. So this line is very important. This line, it is very much important. Okay, then the enthalpy and entropy values they have given in the table for -20 as well as 40 degrees Celsius. So suppose this is the TS chart. So this is the TS chart. So ideally what we have like, it will go on the top. So this is the general TS chart, TS cycle, vapor compression refrigeration cycle TS diagram. This is the entropy, this is the temperature. So this is the anti-clockwise cycle. But here if you read this line, the refrigerant enters the condenser as saturated vapor. That means this cycle is modified for the question as this one. So it enters the condenser, that means this point it is at saturated vapor. Then it leaves the condenser as saturated liquid. That means this is a straight line and directly this is the saturated liquid line. Then it comes like this and then horizontal. So this is the modified TS as per the conditions given in the question. Suppose this is 1, 2, 3, 4. What we have to find? We have to find the refrigeration effect. They have given the mass flow rate. So refrigeration effect will be equal to mass flow rate into delta H, that is H1 minus H4. Okay, now we have to find the value of H1 because it is not known in the question. H2 value is given. How H2 value is given? H2 corresponds to higher temperature, that is the condenser temperature corresponding to saturated vapor, that is H2 value is 200. Similarly H3 value and H4 value, those will be same. So H3 value will be equal to, because it is saturated liquid, so H3 value corresponding to 40 degrees Celsius, it is equal to 80. And we know from isenthalpic expansion that H3 it is equal to H4 equal to 80. Okay, only value what we are missing is H1. How we have to find H1? So let's see. So we know that in ideal condition it is isentropic compression in the compressor from 1 to 2. So we can assume S1 equal to S2. Okay, now if I write other way around, that or I'll write like this only. So S1 value will be equal to So S1 value will be equal to SF, that is S of, and that is the saturated fluid entropy, that is equal to 0.07 at minus 20, because we are dealing with minus 20 degree Celsius line, evaporator temperature line. So it is equal to 0.07 plus X into SFG. SFG will be nothing but SG minus SF, that is 0.7366 minus 0.07. 7366 minus 0.07. This is equal to S2. S2 it means that at plus 40 degrees Celsius, or the condenser temperature, what is the saturated vapor entropy? So saturated vapor entropy corresponding to 40 will be 0.67. It is equal to 0.67. So this value, if you take this side, so it will be equal to, X will be equal to 0.6 divided by 0.7366 minus 0.07, that is 0.666. So if you solve, this value will be equal to 0.90. So X value is 0.90, or the dryness fraction at this point 1, it is 0.90. So you note this value, then I'm erasing this one in order to solve further. So we can note the value of dryness fraction equal to 0.9. Okay, so dryness fraction equal to 0.9, that is X equal to 0.9 we can keep, and we have to find the value of H1. H1 will be equal to nothing but HF plus X times HFG. HF will be equal to corresponding to minus 20. HF corresponding to minus 20 is, see here, 20. So we can write 20 plus 0.9 times HFG. HFG is nothing but HG minus HF, that is 180 minus 20, that is 160. If you solve this, you will get 1. So if you solve this, you will get into 160 plus 20, that is 164. 164 kilojoule per kg, that is the value of H1. Okay, H1 you got, so I am erasing everything now. H1 value is 164 kilojoule per kg. H1 value is 164 kilojoule per kg. What we have to find? We have to find the refrigeration effect. So I already told refrigeration effect is 0.025, or the mass flow rate times the H1 minus H4. H1 you already calculated just now, 164 minus H4 value I have told earlier, it is equal to H3, and H3 is equal to 80. So if you solve this, you will get 2.1 kilowatts. Let me solve just to recheck. Yes, so it is 2.1 kilowatts. Answer A. This is the answer, A part. Okay, 2.1 kilowatts is the net refrigeration effect. Then what we have to find? We have to find the COP. COP is nothing but net refrigeration effect upon the work input, that is equal to refrigeration effect you already calculated, equal to 2.1 kilowatts, and the power input, it is equal to mass flow rate times H2 minus H1. This you can keep 2.1 kilowatts upon mass flow rate 0.025. H2 minus H1. H2 will be saturated vapor enthalpy corresponding to 40 degrees Celsius, that is 200. into 200 minus h1. H1 you already know, you have calculated, that is 164. So if you solve this, you will get 0.025 if you multiply with 200 minus 164, that is 36, then 2.1 divided by 0.9, so you will get 2.33. So this value came out to be 0.9, so it is 2.1 divided by 0.9, that is equal to 2.33. This is the answer. So part A answer is 2.1 kilowatt, part B answer is 2.33 kilowatt. 2.33 without any unit. COP doesn't have any unit because kilowatt get cancelled. Okay. So this is the question for vapor compression. Let's move on to the next question. So guys, I hope the video was very helpful. If the video was helpful for you, please press the like button, please share the video, and if you are new to this channel, please subscribe and press the notification bell. If you have any video topic that you want me to make a video on, please send me your video topics, suggestions, feedbacks, questions, etc. on the email ID that is displayed on the screen, mecengineeringexplained216@gmail.com, or you can send a hi to this mobile number on WhatsApp, +91 9971 825851. So guys, again, I will be seeing you in the next video. Till then, take care.